Suppose you're an 11-year-old child sitting out on your front porch, watching the beautiful sunset and enjoying your delectable jam sandwiches. As you admire the blazing golden rays pierce through the horizon, suddenly an F5 tornado suddenly charges towards your house out of nowhere, destroying everything in its path. But your mother screams frantically to tell the other kids to get out of the house before it is swept away and crushed to little bits. You're busy trying to figure out what is happening to that poor jam sandwich as it is scooped up to the center of the tornado. Is it going to fly left, right, deconstruct into bread and little bits of flying jam? Who knows? More importantly, how much can you know about the poor little sandwich? This is where we move on to chaos theory.
The intuitive idea of chaos lies in the notion of unpredictability. However, we are interested in chaotic deterministic functions, a system which can only evolve or change over time in exactly one way. In these cases, we can think of a mapping as chaotic if the state can be determined, but the margin of error grows exponentially through time. Chaotic systems are everywhere, in weather patterns, planetary systems, even ocean turbulences. Chaotic theory focuses on the underlying patterns and moments of order within a chaotic system. For example, say we're trying to find the exact position of the Earth after some amount of time. While it is theoretically possible to predict its precise location with consideration of every gravitational field affecting the Earth's position, such calculations need to be so accurate to determine positions after longer amounts of time. In mathematical terms, a system can generally be described as chaotic if it fulfills the following three criteria. 1. It must be sensitive to initial conditions. 2. It must be topologically transitive. And 3. It must have dense periodic orbits. What exactly does any of this mean? Let's start from the beginning.
Let's draw a nice circle with a range of real numbers from 0 to 1. Essentially, imagine the circle as a number line, so that we can plot numbers such as half, 2/3, and basically any real number between 0 and 1. Suppose we have a function on this circle which inputs x and returns 2x. Given that the circle repeats, we'll consider the output mod 1. Now, what do we mean by mod 1? Essentially, we are taking the decimal parts of a number, so 2 times 3/5 is congruent to 1/5, and 1 is congruent to 0 mod 1. We observe that for the numbers 0, 1/4, half, and 3/4, after some number of iterations of the function, they all end up as 0. Let's observe another value, say 2/3. When iterated, it seems to move to 1/3, then back to 2/3, then back to 1/3. We call this a cycle, specifically a 2 cycle, because it takes 2 iterations to get back where we started. Picking a point such as 0 yields a 1 cycle, that is, a cycle that takes 1 iteration to get back to the same number. For those who know graph theory, yeah, we kind of stole your notation, whoops. However, if we start at something very close to half, say half plus epsilon, where epsilon is some small number like 0.01, even after a number of iterations, the value will never reach 0, and its distance from 0 increases with each iteration. While this example isn't a chaotic system, it gives a good idea what sensitivity to initial conditions looks like. To see in better detail, let's look at some pendulums.
This is a double pendulum. It's a normal pendulum, but an extra little pendulum attached to it. This system exhibits the idea of sensitivity to initial conditions much better. To see this, let's place 2 double pendulums in the exact same position, but with a slight change in angle. Can't see the 2 different pendulums? You'll see them soon enough. Oh, look! You can see 2 pendulums now. If you look closer, you can see the pendulum staring back into your soul, crying out to be put away from all this pain. They are diverging quickly, just like my sanity diverging from my mind. Oh well. This is what's known as sensitivity. Even a slight change in the initial conditions can lead drastically to different evolutions over time. Let's head back to the world of mathematics to discuss the next element of chaos, topological transitivity, or otherwise known as topological mixing.
these two big words may seem scary, but compared to being crushed by a falling tree, it's really not. To put it in the most utterly intuitive way possible, a function f is topologically transitive if, given any two intervals u and v, the exister k which is an element of z plus, such as f of u iterated k times intersect v is not equal to the empty set. Let's think back to the tornado example. Since a tornado is moving so fast, parts of the jam sandwich can end up anywhere within the tornado, and the whole sandwich isn't stuck in one spot. So, some of the jam might be near the bottom of the tornado, while the slices of bread might be thousands of meters up in the air. Basically, nearby points eventually get separated and flung out to much larger distances, so they don't necessarily stick together in one localized clump. Intuitively, if a map is topologically transitive, then given a point x in the region V, there exists a point y close to x whose orbit passes through V. We'll talk about orbits later on. For those who know a little about set theory, this implies that it is impossible to decompose the system into two open sets. We will move shortly to the final point, dense periodic orbits. However, first, we would like to introduce the idea of attractors and repellers, otherwise known as sinks and sources.
Let's draw a simple graph, y equals x squared. Now let's observe, like we did with the circle, how things change when we iterate the function. When we evaluate the function over and over again, at the point 0, we can see that it in fact stays exactly where it is. 0 to the power of 2 is 0, 0 to the power of 2 is 0, 0 to the power of 2 is 0, etc. Therefore, we can call 0 a fixed point. This is the same as a 1 cycle. We can find all fixed points by asking ourselves, when does f of x equal x? Or in other words, what are all the solutions to y equals f of x and y equals x? Graphically, this is equivalent to finding all the intersection points between y equals f of x and y equals x. Graphing this line on our parabola, we find ourselves another fixed point, 1. Check for a minute that x equals 1 is a 1 cycle, by manually iterating the function. However, this point has a different property than our other x equals 0 point. We can illustrate this using a Cobweb diagram. This diagram is simple. All we do is start from any point along our function and iterate it by drawing a horizontal line towards our y equals x line. Then we draw a vertical line back to our function, and the y value of that point is our output after iterating. We can repeat this and it creates a nice looking cobweb shape. Drawing such a diagram for the value half, for instance, sees the lines tend towards 0, our fixed point. Therefore, we call this an attractor, or sink, because it pulls nearby points towards it. We say that the range of the sink is -1 to 1, because all points within this range gravitate towards the fixed point. However, looking at a value like 1.1, we see that instead of gravitating towards 0 or 1, the point flies off to infinity at an alarming rate, much like me after robbing a bank. This is an example of repelling behavior. Specifically, the fixed point 1 forces points nearby very far, hence it is named a repeller or a source. Note that repellers often display sensitivity to initial conditions. If x equals 1, nothing happens, but if x equals 1.001, the value shoots up to infinity. As you can see, the repelling fixed points display sensitivity to initial conditions. However, the range of asymptotic iteration does not fall to every point, but only 0 and infinity. Therefore, it is not topologically transitive, and therefore not chaos. Let's look at the final criterion for chaos, whatever dense periodic orbits means.
Right, so let's go back to our nice little circle with the numbers from 0 to 1 on it. Recall how if we pick a number, say 1/5, we can see how the iteration of our x to 2x mapping changes the value. It jumps to 2/5, then 4/5, then 3/5, and then 1/5 again. We call the set of values that the initial value transverses the orbits of the value when plugged into our function. In this case, the orbit of 1/5 with our fraction is simply the repeating set, 1/5, 2/5, 4/5, 3/5, 1/5, and so on. When an orbit repeats, we call it a periodic orbit, because it has some kind of period. As far as we are concerned, a cycle is a set of points contained within the periodic orbits of some point. We've already seen this term when dealing with the orbits of 1/3, in which we called it a 2 cycle. Numbers like 0 on the circle form a 1 cycle, or an orbit with a period of length 1. So that's the periodic part of a requirement. What about the dense part? Well, in the world of mathematics, there is a legitimate, completely rigorous definition for literally any word that can be spoken or written by the human population. Therefore, it follows that there must exist some annoyingly complex method for defining the word dense. There is. Let us assume that we have an abstractly infinite number of children sitting on a number line. We can say that this number line contains dense children if, given any initial value, a, and an arbitrarily finite small positive value, epsilon, no matter how small you make the epsilon, there always exists at least one child within the interval a, a plus epsilon, which is part of a periodic orbit. Think about that. It also implies that there are an infinite number of children squished into some arbitrarily small space. It's almost like my basic. Let's put the two words together. A mapping contains dense periodic orbits if, given any interval in the space, there exists at least one periodic orbit or cycle. This emphasizes the instability of such chaotic maps, because a point very near to a cycle may lie in a completely different cycle, whatever near means in a continuous space. An interesting corollary of this is that period 3 implies chaos. If any point's orbit is a 3 cycle, then the function must be chaotic. Now that we've covered the 3 requirements of a chaotic system, we present to you the quintessential example of chaos, the logistic map.
Consider the recurrence relation x sub n plus 1 equals r times x sub n times 1 minus x sub n, for all r belonging to the set of real numbers. What does this look like? If we set up a graph with the horizontal axis as the iteration number, and the vertical axis as the value returned, we can plot discrete points along the graph. P sub 0 equals, I'm not going to say this. If anyone wants to see the definition for these points, they are on the screen right now. Plotting this and setting the r value to something arbitrary like r equals 1, we can already see a curve forming. What does this curve represent? Excellent question. It simply shows how a number, the y value of p sub 0, will evolve over time. To show the curve more clearly, we have incremented the x-coords of each iteration by 1 to represent time. This does not look very chaotic, so let's begin to increase the value of r. As we do so, the curve begins to change its shape, rising higher. Okay, so nothing of interest is currently happening until we reach approximately r equals 3. Suddenly, the logistic map seems to split into 2 different branches. It's not obvious that these branches won't meet again, and in fact, they still converge, but once r equals 3.2, we can immediately see that the 2 lines do diverge. This division into 2 is known as bifurcation. Hence, when we start with an initial value of 0.1 and r equals 3.2, we eventually fall into an attracting 2 cycle, the value bouncing around the top and bottom bifurcated paths. Let's travel to the world of Desmos graphing calculator, because not only do value trackers take a long time to render, but it's also easier to see what's going on. Now let's continue to increase the value of r. Almost instantly, we see the graph bifurcates again, now beginning to fall into an attracting 4 cycle. From here on, it rapidly devolves. As we increase the value of r past a certain value, approximately r equals 3.56, the curve plunges into official chaos, as the points wildly dance across everywhere. Let's stop for a minute at, say here. The logistic map successfully satisfies all 3 requirements for chaos. It is sensitive to initial conditions, which can be seen if we just nudge p sub 0 a bit, resulting in a completely different looking set of points. It's topologically transitive, which is almost trivial given the fact that the points are like splayed everywhere. Finally, it contains dense periodic orbits, which isn't obvious at all, but it does, so trust me or check the Wikipedia article. Surprisingly, there are also islands of stability within this. In the graph, when we set r equals 3.83 or 3.84, we can see that it seems to form 3 straight lines again. And if we move around the initial point p sub 0, we see that generally the 3 branches stay. Remember what this means? At r equals 3.84 or 3.83, no matter what the initial conditions are, eventually, under iteration of the logistic map, it falls into a 3 cycle. And there's chaos again. We can actually view this graph a bit differently. Constructing a different pair of axes such that the x-axis represents the value of r and the y-axis are the values asymptotically approached by iteration, we get what is known as a bifurcation diagram. We can actually see where the bifurcations and chaos happen at values of r. At r equals 3, we see it bifurcate. At r equals 3.42, we see it bifurcate again. At r equals 3.56, we see the system rapidly devolve into chaos. And at r equals 3.83, we see chaos move back to stability, forming 3 islands of calm. This should be astonishing. How can a map that seemingly devolves into chaos as we increase r magically restore itself for a brief moment, only to be flung back into chaotic behavior once more? How are we supposed to know?
Here's a quick preview of pain. This is a Lorenz Attractor, a set of 3 differential equations that are bad and hurt my brain. Here they are on screen. As you watch this animation that took 3 hours to render, you may be wondering, what exactly is this crazy 3-dimensional curve that somewhat maybe resembles a butterfly? Well, in the 1960s, a poor Dutch physicist named Hendrik Lorenz was trying to simulate convection currents and simplified it to the following 3 differential equations that we showed before. However, he noticed that when he kept on running the simulation, the results would diverge greatly after a long period of time, i.e. exhibiting chaos. This was due to the rounding error of the computer that he was using to generate figures, and an error of even 0.001 led to a significantly massive change. Well, that's the end of this video for chaos theory. Or maybe not.
Okay, so there really wasn't a point in doing this one, but I guess it's kind of cool. Ordinarily, when you discuss objects such as fractals, we think of chaos. For instance, the Mandelbrot set has been generated with an iterating function, then colored in based on the asymptotic behavior of an initial complex number. It is defined as the set of values that do not diverge to infinity on iteration of the function f sub c of z equals z squared plus c. Either way, Julia sets and other weird fractals are not within the scope of this video, so let's move on to an iterative generator, the chaos game. The idea is as follows. You choose a certain number of points, say 3. Call these A, B, and C. Now that you have them, pick any arbitrary starting point. Now just randomly choose one of A, B, and C. Add a dot bisecting the segment to the chosen vertex from the starting point. The new dot is now your new starting point. Repeat. As you continue with this admittedly boring game, you may notice something forming. It's not my imaginary IQ, it's not the reformation of my sanity, no, it's the Sierpinski triangle. This fractal should look familiar to you. Now, everything about this game may seem chaotic. It's an iteration of a function, it somehow creates a fractal, and even has the word chaos in its name. But in fact, this has nothing to do with chaos theory, which we noticed too late because we made the simulation first and that's why we're showing it here. You can actually see the stability of the entire system if you change the initial point. If we run the simulation again, you can actually see that the fractal remains almost exactly the same. So in fact, the system is the complete opposite of being sensitive to initial conditions. As for topological transitivity, well, the points move to specific locations no matter where you place your initial point, so that's immediately crossed off. Dense periodic orbits? What periodic orbits? As you see, this really has absolutely nothing to do with chaos despite it being called the chaos game.
As we draw to the end of this video, let's just summarize what we learned because that's always good. We defined a system as chaotic if it satisfies 3 properties. If it is sensitive to initial conditions, topologically transitive, and contains dense periodic orbits. What do each of these mean? A system is sensitive to initial conditions if a small change in initial conditions can result in a wildly different output. We illustrated this with the circle taken mod 1, the double pendulum, and the Cobweb Diagram. A system is topologically transitive if any point will eventually go anywhere on the space of iteration. So while the specific function for the Cobweb Diagram isn't topologically transitive, the logistic function certainly is. A system has dense periodic orbits if there exists a cycle, no matter how close you look. This one is particularly hard to grapple with because it does not say that every point must be a cycle, only that there are infinitely many cycles in the space. We touched on the logistic function, an example of a mapping that becomes chaotic after a certain value of r. We also found small islands of stability within the bifurcation diagram, which really showed how, even in the midst of chaos, there could exist moments of peace. We then moved on to the Lorenz Attractor, a set of differential equations on a 3-dimensional space, where we admired the crazy curves that sort of resemble a butterfly's wings. But notice one last thing. Within the 3 criteria, there was never mention of unpredictability, because ultimately, if you have enough precision, and probably a huge computer, even the most chaotic systems can technically be determined. However, as a final remark, chaos theory can tell us 3 things. 1. Fortune tellers are big fat lies, please don't waste your money on them. 2. Predicting the forecast past 1 week is virtually impossible. And 3. Maybe, just maybe, eating an apple a day could possibly save world hunger. Thanks for watching.